So it's time we can start now. Good day, everybody. It's a pleasure to have with us Dr. Niels Gresnik from Xi'an Jiaotong-Liverpool University in Suzhou, China. Niels has been with us before. You know him well. And he's also a member of the OSMU organizing committee for these lectures. And Niels has made some very important contribution in the field of algebraic unification in the use of sedenions. I think he leads the sedenion studies in this subject. And today he's going to tell us some new results, 3 fermion generations and 1 gauge sector with S3 family symmetry in CL10. And there's a very interesting subtitle, an algebraic route from sedenions to the standard model. Great. Please, over to you, Niels.
Okay, thank you very much for that introduction to Jinder and also for the opportunity to give a talk. So I'm not actually in China at the moment, I'm in Thailand. So I'm doing this presentation from my hotel room. And up until 10 minutes ago, I was busy trying to finish this slide. So some of the later slides might look a little bit messy, but hopefully I can get the point across. And if not, I'm sure there will be lots of questions and comments afterwards, and we can discuss further. So yes, as the title suggests, I want to talk about what I've been working on for a few years now, which is to try and represent the 3 generations of the standard model fermions with the standard model gauge group within a single algebraic framework. Now, lots of other people have also been working on similar ideas. And what I think is unique about the approach that I've taken is to go one step beyond the division algebra, so beyond the octonions, to the algebra of sedenions. And the reason I think that's worthwhile doing is that if you look at the automorphism group of the sedenions, it includes this extra discrete group S3. And so I've been trying to see if this S3 automorphism group of the sedenions can be used as a family symmetry and thereby give an algebraic origin for the existence of 3 generations. So let's see. Here we go. So there's sort of 3 things I want to do. First, I want to show how one can construct algebraically 3 generations of fermions that are linearly independent within a single algebraic framework in such a way that the gauge sector, the gauge symmetries that act on those fermions, is not triplicated. So we want to triplicate the fermion, so we get 3 generations, but we don't want to end up with 3 generations of the gauge group. And part of that is to explain the motivation and the constraints behind the construction. It's taken me a while to sort of get all the pieces together nicely. And so throughout the talk, I'd like to hopefully highlight for you how the construction is very much constrained. And then if we have time at the end, I'm not sure that we will, I'll share some more recent work about how we can also look at the Higgs sector and the Yukawa couplings within this algebraic framework. So I'll start off a little bit with a motivation and with a review of how the octonions have been used to represent 1 generation of fermions with color symmetry or unbroken gauge symmetries. And then what I want to do is enlarge the octonions via the Cayley-Dickson process to the algebra of sedenions, which is no longer a division algebra, and motivate why I think that might be useful in representing 3 generations. And very closely related to the sedenions is the Clifford algebra CL8. Now I'm working in the complex Clifford algebra because things are a little bit easier. And then what I want to do is embed this S3 sedenion automorphism group into this CL8 Clifford algebra. And then I want to construct 3 independent generations and one common unbroken gauge sector. Then if I want to include the weak sector, so the SU2, I found that I must enlarge the algebra to CL10. I was not able to do that in CL8, and I'll highlight why that was not possible. So then I'll present the full model, which is based on CL10 and how all the gauge generators are defined and all the fermions. And then if we have time, I will talk a little bit about the Higgs maps and how we can understand how it gives rise to two Higgs doublets. So the goal then is to represent the gauge structure of the standard model and just have a single gauge group that acts identically in all three generations, or all three families. Whereas for the family structure, the generation structure, what I want three generations, which is what we observe, and I want them to be linearly independent. And so the question I've been asking, and I'm not the only one that's been asking this question, of course, is whether we can represent this structure that we observe algebraically. And in particular, is there an algebraic origin for the existence of three generations? So the first is that the first thing I'd like to mention is that the division algebras, so there are four of them, the real numbers, complex numbers, quaternions, and octonions, they're closely related to Clifford algebras. And so if we let a division algebra or a tensor product of division algebras act on itself from the left or from the right, then we can generate certain Clifford algebras. And I'll review this in a little bit more detail in a minute. And then what we're going to do is we're going to represent the fermion subspaces in terms of minimal left ideals of these Clifford algebras. And the gauge symmetries, they're going to correspond to unitary transformations that preserve the underlying Witt decomposition, which you use to construct those minimal ideals. And for the gauge transformations, we're going to take them to act initially via commutation. But what we would ask is that in the end result, the commutator actually reduces down to just a one-sided action. And then because I want to use S3 as a family symmetry, I want to make sure that the physical gauge generators are invariant under this S3 family symmetry. So here's sort of a diagram of what I'm trying to do. So here we have three fermion sectors represented by the curly S's, and they're related to each other. They're permuted by S3, whereas they all share one common gauge sector. So I want to make sure that the gauge sector itself is not triplicated, so that we don't end up with three generations of gauge bosons. Now, there's quite a long history of using the octonions to represent one generation with color symmetry or electrocolor symmetry, which you can see here. And they all use a slightly different approach. I don't want to spend too much time on this. So just to review, one of the possible constructions is if you take two elements of the octonions, then you can define the left action of A on W. So that's represented here. Oops, let me just go back here. And what happens is that although the octonions are non-associative, if we look at these different maps, these L subscript A's, they generate an associative algebra. And this associate algebra is much larger than the octonion algebra itself, because the octonions are 8-dimensional. But if you look at all these different endomorphisms, which is what they are, they generate a much larger algebra. And that turns out to be a Clifford algebra. So each such left action corresponds to an 8x8 matrix. And if you use the octonion basis elements, then you can find that they anti-commute as left actions, and they give you a representation of the Clifford algebra CL06. Then once you complexify that, that would give you the complex Clifford algebra CL6. Now, why do you complexify it? Is because when you complexify it, it's really easy to define a Witt basis that satisfies the standard anti-commutation relations. Did I include? I forgot to include what the Witt basis looks like explicitly, but I do it for CL8 later. So the way that you can then build up the minimal ideals is to first define some primitive idempotents. And so I've got 2 here, but in total they're actually 8. And then you can construct the minimal ideals by left multiplying any element of the algebra onto those primitive idempotents. And so here we have 2 minimal ideals, SU and SD, and each of them are going to be 8-dimensional. Now, if you look at the unitary symmetry that preserves those ideals or the underlying Witt basis, then that gives you a U3 subalgebra of spin 6. So spin 6, that's the algebra generated by all the bivectors of the Clifford algebra CL6. But only a U3 subgroup of that actually preserves the underlying Witt basis or the maximally isotropic subspaces W and W dagger. Well, within that U3 algebra, you can then define the SU3 color generators, as I've done here, with the lambda. The lambdas are just the Gell-Mann matrices, and the electric charge can be defined in terms of the number operator. And then you can find that under that symmetry, those 2 minimal ideals transform as one generation of particles and antiparticles. And there's a really nice presentation of this in great detail that can be found in Nicole Furey's PhD thesis. So that's what these last few slides I've taken mostly from her thesis. So now I've been wondering, can we go one step beyond the octonions? So if the octonions do a good job in describing one generation, if we go beyond the octonions, could we then describe 3 generations? Now you can generate all of the division algebras starting from the real numbers via what's called the Cayley-Dickson process. So that generates the complex numbers from the real numbers and the quaternions from the complex numbers and so on. But that process itself does not stop with the octonions. It actually continues indefinitely. So if I apply it once to the octonions, I then end up with a 16-dimensional algebra, which is called the algebra of sedenions. And so I'm using here as a basis for the algebra, the identity, and then S1 to S15. So we have 15 imaginary units. Now, I could provide the multiplication table for the sedenions, but that's not particularly useful for what follows, because very soon we're actually going to go to a Clifford algebra. So it's important to remember that the sedenions themselves, they're not a division algebra, and they're not associative, they're not commutative, and they're not even alternative. At the same time, if we look at existing constructions based on octonions or tensor products of division algebras, such tensor products of division algebras are also no longer division algebras. So for example, if you look at the complex octonions, that's no longer a division algebra. Now, the reason that you can represent one generation in terms of the octonions with SU3 color symmetry is because the automorphism group of the octonions is known to be the exceptional group G2. And that contains SU3 as a subgroup, as a maximal subgroup, I believe. Now, if you look at the automorphisms of the sedenions, then again, you just get this G2 group, but you also get this extra factor of the discrete group S3. And so the question I've been asking is if we can use this S3 to motivate the existence of 3 generations. So the question then is, well, how do we exactly do that? And how do we embed those S3 automorphisms into the appropriate Clifford algebra, which turns out to be CL8? And then how do we choose the spinor subspaces to represent the fermions in such a way that when we apply the S3 symmetry, it generates three linearly independent generations? And at the same time, how can we ensure that the gauge sector is not triplicated? So just like for the octonions, we can consider the left action of the sedenions on themselves. And so we get these left action maps. And each such map corresponds to an endomorphism. And that can be written as, in this case, a 16 by 16 real matrix. So if we take the first 8 sedenion basis elements, the imaginary ones. So the first 7 are just the octonion ones. And then we have the first extra one, which is S8. If we consider the left actions of them on a general sedenion, then we find that they anti-commute. And in fact, they generate the real Clifford algebra CL08. So now if we complexify, then we end up with complex CL8, and we can define a Witt basis, which is what I've done here. So we have 4 Witt pairs, and they satisfy the standard anti-commutation relations. From them, we can then define 16 primitive idempotents, which are here F subscript epsilon, where the pi j's, they are just simple idempotents. So the primitive idempotents, they're all rank 1. And then from them, we can build up the 16 minimal ideals of the algebra just by left multiplying any element of CL8 onto it. Now, it's quite useful to actually adopt a particular matrix representation of CL8. And so for this one, I've chosen the one I've used here, where I've represented E1 to E8, as well as the pseudoscalar, which I've called omega 8. And the reason I quite like this basis is because then all the primitive idempotents come out as rank 1 projectors with just matrices with one non-zero entry on the diagonal. So that means the first minimal left ideal would correspond to the first column of the matrix algebra, and the second minimal ideal would be the second column, and so forth. Well, for the sedenions, we have 15 imaginary units. And so far, I've used the first 8 to generate a basis for CL08. That means that the remaining 7 sedenion imaginary units should then correspond to some CL08 multivector, because they're also going to be 16 by 16 matrices, and so it must be possible to represent them as some element of the Clifford algebra. And it turns out that you can write these remaining sedenion left actions in terms of the G2 invariant 3 form, which is given here by phi. And a simple way to write it is in terms of these BI's here at the bottom. And then we can write the left actions of the remaining 7 sedenion basis units as such. So just to give one explicit example on the next slide, for example, B1 would be this 4-vector term, and then G1 would end up being this term here. And so we see that G1 to G7, which are the sedenion left actions of S9 to S15, they're actually even elements in the algebra in CL08. And it turns out that those 7 GIs also anti-commute with each other, and they also anti-commute with E8. Yes, that's right. So we can have another basis for the same algebra CL08 in terms of G1 to G7 together with E8. So the basis for the algebra is not unique. However, if we try to look at the anti-commutators of the G's with the E's, then they don't satisfy very nice relationships. So that's where the algebra can become a little bit complicated. So as mentioned earlier, the sedenions carry an S3 automorphisms generated by psi and by epsilon. And so one of the things I want to do is to embed this symmetry, these automorphisms of the sedenions, into the complex Clifford algebra CL8 in such a way that they correspond to automorphisms of the algebra. So the question is, how do you do that? Well, it turns out that there's several different ways to do it. However, there are a few constraints for what I want to do. So some of the conditions are that we want to make sure that the order 3 symmetry, psi3 in particularly, mixes the octonion direction, so that's E1 to E7, together with the new sedenion directions, which are the G1 to G7. And we want to make sure also that this S3 symmetry is going to commute with the G2 action, but not with the larger spin 7 action. So in other words, we want to make sure that the automorphisms of the sedenions is this G2 times S3. So we want to make sure we can embed that structure into the Clifford algebra. And we want to make sure that the S3 that we choose fixes the color algebra, the SU3 color algebra pointwise. And we also want to make sure that it produces 3 linearly independent spinor sectors. Then a little bit later, when we extend to CL10 and we embed this S3 symmetry into CL10, we want to make sure that it also fixes the weak generators as well as the hypercharge. And so we want to make sure that we can reproduce the standard model spectrum and a rank 96 orbit, which is going to be where we have the 3 generations living within the algebra. So here is the only choice for psi3 that I could find that satisfies all those conditions. And so it looks a little bit messy, but we can see that if we act on the CL8 basis, then it mixes these EIs with the GIs, but it also contains these extra terms. It mixes the EI with the E8 and the GI with the E8. But psi3 fixes the identity and it fixes E8. And then what you find is that those transformed elements satisfy the same anti-commutation relations as the original CL8 basis. And so that means we get that the automorphism, or the psi3, extends to an automorphism of the whole Clifford algebra. It also means that these transformed elements, psi3 of EI, they correspond to just another basis for CL8. And because we have an algebra automorphism, it means we can determine also what the action of psi3 on these other elements GI is. Now it's worth quickly mentioning that psi3 is not a spin 8 transformation because it doesn't preserve the 1 vectors. And it does not preserve the Z2 grading of the Clifford algebra either. Now for the remaining order 2 automorphism or generator of S3, I use the grade involution. So it just changes the sign of all the 1 vectors of CL8. And then because the GIs, they were even elements in the algebra, they are fixed. And then you can check that psi3 and epsilon generate S3. And then, of course, we can also check the effect of epsilon on the Witt basis and on the primitive idempotence. And we find that they fix the primitive idempotence, but change the sign on the Witt basis. Now, here's where the explicit matrix representation comes in quite useful. So if we look at the first primitive idempotent, that's just the matrix with a single one in the first column and first row and zeros everywhere else. And then just for comparison, I've also included another state here, which would be a state in the first minimal left ideal. Well, we can then work out what their images under Psi3 look like, and they're given in the two boxes here. Now, the reason I included these explicitly is that we can see that the transformed primitive idempotent and the minimal ideal state, they only find support in two columns. That is the first column and the 14th column. Because E14, 14, that's just another primitive idempotent. So what that means is that the first and the 14th minimal ideals, or the first column and the 14th column, they form a closed subspace under this S3 action. And one easy way to see that is to apply the Psi3 generator again to the primitive idempotent. Then if you can then form this invariant sum here, where we have E11 plus its two transformed versions, and we add them together. And then that gives you the sum of the first and the 14th primitive idempotent. And so then that one is going to be S3 invariant. And the same is also true for another primitive idempotent, E99. So that's the ninth column. If we apply the Psi3 symmetry to the ninth primitive, to the ninth minimal ideal, then it mixes the ninth and the sixth minimal ideal together. So what that means is that we find certain closed subspaces under this action of S3. And so we have the first and the 14th minimal ideal form a closed subspace, and the sixth and the ninth minimal ideal form a closed subspace. Now the same is true for the remaining minimal ideals, so they also pair off and give a number of invariant subspaces. But the four that we will be using is the I1, I14, I6, and I9. So far we have two algebraic ingredients. We have the Clifford-algebraic CL8, which we get from the sedenions, together with this S3 symmetry, which also comes from the sedenion automorphisms, which we've embedded into the algebra CL8. So now what we want to do is we want to identify three fermion subspaces so that they are linearly independent and that they all transform correctly under the unbroken gauge symmetry. And we want this gauge symmetry to be fixed by the S3 action. So just like for CL8, we had that the Witt preserving symmetry was U3. This time, the Witt preserving symmetry is the Lie algebra U4, which is a subgroup of spin 8, which is what the bivectors of CL8 generate. However, we find that not all of U4 is invariant under S3. Only the unitary subgroup SU3 is invariant. So now we can just define the SU3 generators, just like we did before, in terms of the Gelman matrices, and you can check that those are in fact invariant under the S3 action. Like I mentioned before, I'll skip over this slide, but I'm taking the action of the gauge generators to be that of the commutator. And the reason for that is that it preserves the primitive idempotents. Now, if we take a minimal ideal in CL8, and we just write it as x is equal to y times the primitive idempotent, then if we calculate the commutator, we can write it out as written here. Now, I want the action of the SU3, the commutator action, to reduce down to just a left action. So that means I want the second term on the right-hand side to be 0. This only happens for some of the primitive idempotents, not for all 16 of them. In fact, it only happens for 4 of the primitive idempotents. So that's here. Yeah. So the SU3 action from the right annihilates four of the primitive idempotents, and they're exactly the first one, the ninth one, the 14th one, and the 16th one. And that's the reason why I highlighted these before. So if you remember, it's this first one, the E1,1 and the E14,14. Those two minimal ideals that they generate forms a closed subspace on the S3. And it's the same for the other two, for E9,9 and E6,6. So the minimal ideals that they generate are also closed under the S3 action. So only on those subspaces does the SU3 commutator reduce down to a left action. So for that reason, I want to choose my fermions to live inside those four minimal ideals. The four minimal ideals generated by these four primitive idempotents. So one option would be just to take one of the, say, the first minimal ideal with a 16-dimensional, and then say, identify that with the first generation. However, that's not going to work because on the S3, we then only get a 32-dimensional subspace. So that means it'd be impossible to get three linearly independent fermion sectors. So for that reason, instead, I pass to the 8-dimensional semi-spinors. So I select 8 states within the first minimal ideal in such a way that if I apply the S3 symmetry, or when I apply Psi3, the order 3 generator, then it gives me linearly independent generations. So I choose the first sector to be the even semi-spinor. So that means all the even terms of the first minimal ideal. So that's an 8-dimensional space. And then under the SU3 color action defined earlier, that semi-spinor transforms as would half a generation. So we get a triplet, an anti-triplet, and two singlets. So then if we want to include the remaining states, we need to choose another 8-dimensional space. So there's sort of two candidates that would work. One is to right multiply the I1 plus by A4, or to multiply it by A1, A2, A3, A4. Both of them would work. I've chosen to use the first option. So I use the odd graded elements of the 9th minimal left ideal. And then they also transform as a triplet, anti-triplet, and two singlets. And so now if we identify the first generation space with S1, so the direct sum of those two semi-spinor spaces, then once we apply the Psi3 automorphism, so that's the S3 symmetry, then we end up with the remaining two generations, and they're all linearly independent. So the dimension of the space that they generate is 48. So that's all linearly independent. And the color, as I mentioned before, the color generators are fixed by the order 3 automorphism. And then that means that all three generations are going to transform exactly the same. So we already worked it out for the first generation, and those remaining two generations are going to carry the same color representation. Well, then it remains to also include the electric charge generator. So in CL6, one can use the number operator, but that doesn't work in CL8. So here, what I've chosen to do is to use the commutant of SU3 in SU4. So that's this Q1 here. The problem with that, however, is that Q1 is not invariant under Psi3. So in order to obtain an invariant version of that, I take the orbit over Psi3. So we see here in the boxed equation that we have this Q, which contains three terms. And this Q now is invariant under psi3 and also under epsilon. And then it turns out that Q assigns the correct electric charges to all the states in our three generations. So that seems to work for the electrocolor symmetry. Everything works so far. But what is still missing is the SU2 symmetry and the hypercharge. Now, there's not enough room within CL8 to include them. So for that reason, I decided that I should enlarge the algebra to CL10. That then gives us an additional Witt pair, which is enough to include the weak sector. So when I try to include it in CL8, the issue is that you can no longer get linear independence of all three generations. So what I do is I use the graded tensor product realization of CL10, and I just embed the original CL8 basis vectors via tensor product with the 2x2 identity matrix. And I'm slightly abusing the notation here. So again, for CL10, for the basis, I'm just going to use the EIs again. Well, once we know the action or how to embed the CL8 basis into CL10, then we can also check what happens to the Witt basis of CL8 and to the SU3 symmetry generators. So then we only need to write down the remaining two generators, E9 and E10, which I do in terms of these Pauli matrices. And then I can define the fifth Witt pair. And then what we see is that the embedded CL8 generators act blocked diagonally on the upper and the lower 16 by 16 component sectors, whereas E9 and E10, they have this off diagonal. And so they map those two sectors into each other. And so now once we are in CL10, we're talking about 32 by 32 dimensional matrices. And we can then also embed the S3 generators into CL10 because their action on the Pauli matrices is trivial. So it doesn't affect the CL2 factor in CL10. However, the action on E9 and E10 is non-trivial because the definition of E9 and E10 includes this factor of omega 8, which you will recall is the CL8 pseudoscalar. And that pseudoscalar is not fixed by S3. So that means that E9 and E10 themselves are not invariant under psi3. So we extend the CL8 Witt basis with this fifth pair now, and then we have this larger anti-commutation, these anti-commutation relations for the full Witt basis. And now we can define the 32 primitive idempotents, and we can write down the 32 minimal left ideals of CL10. Now it is checked that we can embed the primitive idempotents that we had before in CL8 into CL10. And then this closed subspace structure that we found in CL10 with two of the minimal ideals form a closed subspace under S3, this extends to CL10. And in fact, now we get four closed subspaces under S3, which are listed here. And so this time, each of them is 64 dimensional. Have I got that right? Yes. Because each minimal ideal is 32 dimensional and two minimal ideals form a closed subspace under the S3 action. So now we want to repeat the construction from before. That is, we want to identify the gauge symmetries and we want to identify the fermion sectors such that we can get three linearly independent generations, this time both weak doublets and weak singlets, and in such a way that we can include the SU2 gauge symmetry, the weak symmetry that's left-handed, as well as the hypercharge. So first, let's take some 8-dimensional color multiplet, and let's call it V1 plus, which is going to be some subspace, some subset of the first minimal ideal in CL10. Now at the moment, I'm not choosing exactly yet what V1 plus must be, which states they are. I'm just saying that they must transform as two singlets plus a triplet and an anti-triplet under SU3. And then let's define the remaining three sectors as V1 minus, U1 minus, and U1 plus. And we can obtain them by right multiplication by A5, A4, or both A4 and A5. And then we find that they live in 4 of the other minimal left ideals. And because the SU3 commutes with the 4th and the 5th Witt basis elements, A4 and A5, that means that all 4 of those spaces are going to transform the same under SU3. And so here we have a diagram where I'm going to have V1 plus and V1 minus to be the weak doublet states, and then U1 minus and U1 plus, they're going to be the weak singlet states. And then what I'm going to do is define the first generation as the direct sum of those 4 spaces. And so the complex dimension of that space is going to be 4 times 8, which is 32. And then we want to choose these sectors in such a way that when we apply S3, we end up with 3 such sectors that are linearly independent. So we have quite a lot of requirements that we have to satisfy at the same time. So we want to make sure that all the sectors are color compatible so that they give the right transformation on the SU3. We want to make sure that the color commutator becomes, or that the commutator with SU3 just becomes a left action. We want to make sure that V1 plus and V1 minus are the doublets, whereas U1 minus and U1 plus, they must be annihilated by whatever SU2 action we introduce. And we want to make sure that the weak action is compatible both with the color SU3 and with the S3 family symmetry. So that means we need to make sure that the SU2 commutes with the SU3. And then we want the combined Psi3 orbit over all the fermion spaces to have rank 96, so that all the 3 generations are linearly independent. And finally, we need to make sure that the electric charge generator and the hypercharge give the correct standard model assignment, so we get all the correct quantum numbers. So let's see how to do that. When we want to include the SU2 weak symmetry, we need to make sure that it only acts on the doublets and not the singlets. So to make sure it doesn't act on the singlet, we need to introduce this S3-invariant projector. And so I've called that P, and we can see immediately that this is invariant actually, because the term in the parentheses here, this F plus 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 and F minus minus plus, that was invariant in CL8. And so now all we're doing is we're left multiplying it by the 2x2 identity matrix, which is also invariant. So that then gives us a sum of 4 primitive idempotents. And so that's a projector. It's a rank 4 projector. And explicitly, it's this E11, E1414, E1770, 17, and E3030. And then we see that, this projector is fixed by the S3 action. And importantly, it also commutes with the SU3 action. And it also commutes with the 5th Witt pair. And so that's going to be really useful in defining the SU2 generators. So now we're in a position where we can define the SU2 generators, which I've done here. And so although, as I mentioned before, the omega 8, the CL8 pseudoscalar, is not fixed by Psi3, when we look at the combination E9 times omega 8 and E10 times omega 8, then they are fixed by S3. And so this copy of SU2 is invariant under the S3 family symmetry. So now we've come to the point that we can identify the fermion sectors. And let me just check the time. And I'm not spending too much time. So now I'd identify this V1 plus subspace to be this here. So it's part of the first minimal ideal, and it's 8-dimensional. And these states, the selected states here, they contain a triplet, an anti-triplet, and two singlets under SU3. Now, it's worth noting that this is not simply the embedding of the semi-spinor that we used in CL8. If you try to embed the semi-spinor I1 plus that we used in CL8 directly into CL10, then the construction does not work. And the reason it does not work is because of this projector. Then the commutator with SU2 does not reduce to a one-sided action. So, yes. So we have to be the difficulty is in choosing the singlets for this first space. So to choose the SU3 singlets, in total, there are how many? There are 8 of them, but 4 of them are already killed off by the projector. And so there's only 4 left, and then you have to choose 2 out of the 4. But we also have to make sure that when we apply this S3 symmetry, that we get linear independence across the generations. And this doesn't happen if you just choose 2 arbitrary singlets. So there's only about 1 or 2 combinations that work, and the choice I've presented here is one of them. So there's not actually much freedom here in how you choose this space. Well, once we've chosen this V1 plus, then we can identify these other 3 sectors. So to have the doublets and the singlets. And then the action of SU2 on the singlet sectors is going to be trivial because of this projector P. So if we just go back, we see P here. It's going to select the first, the 14th, the 17th, and the 30th columns. Whereas the weak sectors, the singlet sectors here, they live in the 9th and the 25th minimal ideals. And so they are blind to this SU2 symmetry. So the action is going to be trivial. Whereas if we look on the isospin up and the isospin down states, so on the doublet states, so that's in V1 plus and V1 minus, then the commutator action of SU2 reduces to a right action. So this is different to the SU3 action. The SU3 action reduces to a left action. And so that is a transformation within a given ideal. Whereas for the SU2, the commutator action reduces to a right action. And so the right action gives you transformations between different minimal left ideals. And so that's what we find here. Now we need to be a little bit careful with the electric charge generator because the one that we used before for CL8 is not going to work in CL10. And that is because it does not distinguish between the weak partners, because the 2 weak partners are related just by right multiplication by this A5. And so since the electric charge generator only lived in CL8, it's going to be blind to this A5. And so it's going to give the states in the isospin up and the isospin down sectors the same electric charges, which we don't want. So that means we need to make a correction to it, which we can do here. And so that's at delta Q5. And that gives a correction to the electric charge. And this correction is invariant under Psi3. And so I have this updated electric charge generator now Q prime, which is invariant under S3. And I also here then include the hypercharge, which is also invariant under S3. Oops. And so we have this first generation isospin up subspace, which lives in the first minimal left ideal of CL10. And we have the first full generation as four of these spaces that live in four different minimal ideals. So it selects 8 states in four of the minimal ideals. And then we generate the second and the third generation by applying this order tree S3 generator to the first generator, to the first generation. And then if you check, you find that the three generations are completely linearly independent. So you get 96 states that are linearly independent. Whereas all the gauge symmetries, all the gauge generators for SU3, for SU2, and for the hypercharge, as well as for the electric charge, they're all fixed by this S3 symmetry. And so in this way, we end up with three fermion generations that are permuted by psi3. So they're related to each other by the S3 symmetry, whereas the gauge sector is fixed by this family symmetry S3. And then an additional check you can do is that if you look at the gauge generator space, that is 12-dimensional, and all those generators are also linearly independent from the fermions. So in total, the fermions give you 96 dimensions, and the gauge space gives you 12 dimensions, and they're all linearly independent. So you have 108 linearly independent algebraic objects. Let's see how we're doing for time. I've got a little bit of time. So I'll finish by talking a little bit about the Higgs sector, how we might be able to include Higgs doublets into this algebraic model. And this is where I sort of run out of time to finish all the slides. So it's, apologies if everything is not perfectly clear. So from before, we found that if we take the isospin up states in the first generation, that's this V1 plus, and then we multiply on the left by A5, then we get the isospin down states. And likewise, we can multiply the first singlet state by A5, and that gives the other singlet state as well, or the other singlet subspace. So we see that right multiplication by A5 changes the weak isospin for the doublets. And right multiplication by A4 moves the doublets to the singlet spaces. And so we can use this to include appropriate Higgs channels. So if we take two primitive idempotents, Fa and Fb, and let's say that they support the source and the target ideals, then a Clifford element, we can take it to act from the right. So we can take a Higgs map to be some H that takes us from the ideal A, or the ideal that's built on the primitive idempotent Fa, to the primitive idempotent Fb. And we can do this via a right action, just like we did for the weak gauge symmetry, the SU2. And so then here in the diagram, we can see that for the down type targets, we can look at the isospin up and the isospin down sectors, and we can map both of them into one of the singlet sectors. And we can do the same if we want to map it into an uptype target, into the other singlet sector. So what do these look like then? How do these Higgs doublets, what do they look like as algebraic elements? Well, it turns out that we end up with two Higgs doublets. And so the first one here is given by this by these two elements, and then the second one is this one here. And both of them transform as SU2 doublets, but they have opposite hypercharge. So one has hypercharge +1, the other one -1. Now the subscript here on the Higgs doublet is to denote that they're the first generation Higgs doublets. And so what we see here is that we get a type 2-like separation of down type and up type Yukawa channels. Now the problem is that these Higgs doublets that I have here, they are not invariant under S3. So that means if we apply Psi3 to them, we would get additional Higgs doublets. So in the end, what I decided to work with was to work with the averaged version. So I average over this Psi3 orbit. So then I end up with Higgs doublets that are invariant under S3. Actually, that's not true. Under Psi3, because they change sign under epsilon. So they're actually in the 1' representation of S3. So, but these two here, they are singlets of S3. And then you can work out the scalar part pairing. So that means if we look at what was it? These terms here, where we wedge Cl10 in between Fa and Fb, and we look at these Higgs types terms, and we take the scalar part of them, then we can produce this mass texture, or this relative texture here, M bar, which has the eigenvalues 3/4 and 3/8. But we should be careful here because this is in a symmetric algebraic limit. So it's not I'm not claiming that this is any kind of mass fit. So what I've done here is I've I have 3 generations of 2 Higgs doublets, and I've combined them, I've symmetrized them over the Psi3 orbit, so that I end up with these invariant versions, which are then invariant under Psi3. So what I have then so far in this model is I have 3 independent fermion sectors, each of which has 32 states in it. And each of them has the correct standard model gauge quantum numbers. And there's only one gauge sector. So the gauge sector is fixed by the S3 symmetry. And I have some constrained internal Higgs maps. And all of this can be verified in terms of matrices by using the basis that I have provided. But of course, there's also still a lot of open problems. One of the things I would really like to do is develop these ideas about the Higgs sectors and the Yukawa couplings, and then to see how can I get the scalar potential and the vacuum alignment. And then at some stage, one would have to break this S3 symmetry. So what I guess what has to be done is one has to look at a singlet and a doublet representation of S3. So the singlet and the doublet, they're irreducible representations of S3, whereas the symmetry that I'm using, or the way that the 3 generations of fermions are permuted, they are not an irreducible representation of S3. Then, of course, a related question is about how can you get realistic masses and mixing, so the CKM and the PM&S matrices, as well as the full spacetime and the Lorentz structure. And another interesting question that I've been thinking about, but I'm not sure how to do it, is what is the relation between what I've done here with S3 and the triality of spin 8. So there's some other models, one by Nicole Fury, that uses triality, for example, to get 3 generations. And also the recent paper, or last year, by Quinta, which also looks at spin 8 triality and uses that as the algebraic basis for 3 generations. So I'm not sure how to relate the S3 family symmetry that I use to the S3 that arises in triality. So if anyone has any ideas about that, I'd love to hear about it. And then the other thing that I'm interested in doing next is trying to see if I can use this S3 symmetry as a flavor symmetry, and then to see if it produces anything, or if it has anything to say about flavor symmetry. So these ideas already exist in the literature where people take an S3 uh, group as a flavor symmetry. But what exists in the literature, this S3 is just put in by hand. Whereas I think the way I've done it, this S3 ultimately is motivated from these automorphisms of the sedenions. So I'd like to develop those ideas further. And finally, I would just really like to thank Yannick because he spent a lot of time checking uh, every single calculation in the two archive papers that I put up earlier this year. So he contacted me a few months ago and he said he was trying to verify everything. And yeah, so I'm very grateful for him. And he was kind enough to share those Mathematica notebooks that he created on GitLab. So I've just included the links here so that if anyone is interested, you can check all the verifications of the calculations there. And I think with that, the time is almost up. So I will stop there and then hopefully have some questions or comments or ideas or criticisms.
Great. Thank you so much, Niels. That was a very, very interesting talk and definitely a very solid piece of work with much to look ahead. Great. So I already have a comment which I'll read out. No, where did it go? One moment. Yes, the audience is called AJSH. I'm sorry, I'm not able to make out who it is.
That's Andrew. This is Andrew.
Yes, Andrew. Oh, yes, Andrew. Go ahead. Sorry. I'm sorry. I'm so sorry. Why don't you ask it yourself? Yeah.
Yeah. My question is, can you comment on how the pattern of observed masses of the three generations of fermions might be produced? You've emphasized this threefold symmetry, but it's evident that the three generations are not symmetrically the same.
Yes, very good question. Exactly. So what I have at the moment, it treats the way that I treat the three generations, as you said, they're all equivalent to one another. So there's nothing that distinguishes that would make one more massive than the other. So if one looks at the observed masses, I'm not exactly sure how to do it. I think the way to do it is to use the ideas in the existing literature when people look at an S3 flavor symmetry. And what they do then is they look at the irreducible representations of S3. And so the irreducible representations of S3, they're a singlet representation and a doublet representation. And so the idea then would be is to, instead of using this three-dimensional representation, which is what I'm using, is to convert it into the singlet and the doublet representation instead. And then it might be that it makes one of the generations or two of the generations heavier than the other. But this I have not worked out in detail yet. So that's very much speculation at the moment.
Can I follow up on that and ask? There's obviously a big difference between the mass of the neutrinos versus the other fermions. Any
Yes.
ideas in that direction?
No. No is the no is the very short answer. The slightly longer answer would be I would have to have a look at the recent paper by Quinta, Gonzalez Quinta. I think he gave a talk a few weeks ago because he produces these really interesting mass formulas. Now I don't know, Tejinder, maybe you know, the mass formulas that he produces. Does that also include the neutrinos or not?
I think Gonzalo is in the audience, I think.
Ah,
Hi.
Yeah, yeah.
Nice to
Gonzalo, are
meet you,
you
Niels,
there?
finally.
hi, nice to meet you. So I think in your
Yeah,
paper,
so the internet
you
here
have
is
really interesting
deplorable.
relations.
Sorry, I'm in the
Sorry, go ahead.
I'm in the middle of a conference. The internet here is really bad. I might crash at any time. So that's why I didn't say anything. So yeah, you can parameterize the 3x3 Euclid matrices in terms of 3 parameters, and the neutrino masses fit there really wonderfully. But I don't understand why the specific values appear. The values are 2/9 in one of the parameters for charged fermions, and for neutrinos is 2/9 minus pi/12. I have no idea why it works, but it works really well. Apart from that, I have no new insights. Also,
Okay.
great work, Niels, by the way.
Oh,
Great
thank you very
presentation.
much.
Loved it.
So yeah, I don't talk about mass ratios at all. I don't have too much to comment on that because I haven't really studied it in great detail. But I think what we just heard, like I think that's a step in the right direction. So I'd very much like to look into that further and see if what comes out if I do the same in my model.
Thank you. Andrew, something more? Okay, so there's a question from
I would like.
Sorry, Anthony? No, you want to go ahead?
Okay.
No, after the other question.
Okay,
Don't worry.
Anthony, you go ahead, please. Go ahead.
Okay. Yeah, thanks very much for the talk. Very interesting. So towards the end, you were pointing out that you haven't got to Lorentz transformations yet. And this seems quite a big thing not to have in it. Now you're already at CL10. Is this lack of the Lorentz transformations because you haven't got to that bit yet? Or is there not room and you need to go larger?
Yes. Okay. Very good question. I have thought about it a little bit. I can think of a couple of ways to do it, and I'm not quite satisfied, but with the ways that I've come up to do it, that I've come up with. So that's why I haven't included it yet. So of course, one way you could do it is you make the algebra larger, gives you more space. You make sure that this family symmetry acts on it trivially, and then yeah, you can do it. But I think the algebra, as you pointed out, is already quite large. You already have CL10. And there's a lot of space in there that's currently not being used. But as far as I can tell, it's not currently possible to include all the Lorentz symmetries in a way that is invariant under S3.
Okay, so thinking about the size of your space versus,
yes,
say, what Goncalo has been using. So he's been using CL8, and
yes,
he's able to get in all of SU3 and SU2 and Lorentz transformations. And so is that a difference because you're wanting to do it via the S3 sedenions rather than the triality? Does it stem from that, basically?
That's one of the reasons. I think there's two reasons why there's a difference here. So one is because I take this S3 that I want to use as a family symmetry. The second reason is that I start off with the gauge action being via the commutator. So I take this commutator action, and the reason that I do that is because if you just do a one-sided action, say from the left, then in general that does not preserve your primitive idempotent. So it doesn't map a projector to it doesn't map an idempotent to an idempotent in general. And so that's why I'm doing the commutator action. And then I have this additional condition is that on the fermion subspaces, I want this commutator action to simplify to a one-sided action, whether that be a left action or a right action. And I think that tells us something important. So for SU3, it becomes a left action, but for SU2, it becomes a right action. And so they're quite different. So one, the SU3, it gives you a symmetry within a given ideal. But if you only multiply from the left instead of taking a commutator action, then why are you choosing one minimal ideal over any other minimal ideal? You could then take any minimal ideal and you transform exactly the same. But if you take this commutator action, then in CL8 for simplicity, for simplicity, there's only 4 minimal ideals for which the commutator action reduces to a left-sided action. And so that's how I'm selecting where my fermion space must be. Because I impose this additional condition that the commutator has to simplify to a one-sided action. And that eliminates most of the minimal ideals.
The ones that are eliminated, and those that remain. So you end up with this structure. I think it was 1, 9, 17, 25 was a structure. How arbitrary is that? Could you, in the end, have some completely different combination? And if not, why is that popping up?
Right. So is it completely arbitrary? No, definitely not. Are there different possibilities? Absolutely, yes. So
Yes.
one, of course, if you choose a different CL8 basis, then you can mix all the minimal ideals. You can basically get anything you want. So I've just that's why I choose this particular CL8 and CL10 basis, because it's quite simple to see what is going on. So if I look at how S3 acts on it, let me just try to find the slide here. So once I've got my basis and I've defined the S3 generators, then I can work out how does it act on those minimal ideals. And so I find that I get this closed subspace where the whole algebra, so the CL8 algebra, has got 16 minimal ideals and it splits into 8 closed subspaces. Now, I think that structure would be preserved even if you choose a different basis, although those subspaces they won't correspond to specific columns. It'd be more complicated than that.
Okay, thanks.
So I think just to quickly finish off on your question, is that's why I think ultimately I need to go to CL10 and I can't include it all within CL8. Whereas if I were to start by just saying, okay, a one-sided action is fine, then maybe it is possible to do it in CL8. And the other possibility in terms of space-time is to what was I thinking of? Yeah, but was to have this CL10 as like an internal fiber in some manifold, so that the gauge symmetries, all of that lives inside the fiber bundle that you then attach to the manifold. And so then the Lorentz symmetries would be quite different from they'd be different from the internal symmetries.
Okay.
Thank you.
So
Thank you.
if I may
Jason, go
add
ahead, please.
something to that answer.
So, who's that? Gonzalo?
I just wanted to add something to
Yeah, please
Niels'
go ahead.
answer.
Go ahead.
So,
Go ahead. Go ahead.
So if you choose one-sided transformations, you will need the Higgs fields to break the left-right symmetry. If you use the commutator, you'll get just the left-hand side symmetry. That's so it's useful, like you said, because of that. So using the approach that you use, you don't need a separate Higgs to break the left and right symmetries.
Thank you. Thank you. Jason, go ahead, please.
Yeah, I just wanted to make a quick statement. My own model uses CL8, and in that model, what I've done is I've broken the SU3 symmetry by sharing generators between space-time and what you would call the fiber. It might be something worth exploring in your own model to do something similar, because the trouble is these symmetries are great, but then you have to break them somehow to get different masses. But in my case, I was able to generate U2 from U3 just by sharing the generators of space-time with the fiber, which also created the Higgs because of the cosets that come along with that. So it might be worth looking into that. It could be just the lack of space-time in your model that's, you know what I mean, that's not giving you an avenue to break all of the symmetries that would be there otherwise.
Yes, thank you for that comment, Jason. And well, we've had some email correspondence as well, right? And I find your model really interesting because you talk about this space-time, and you have your space-time symmetries, if I understand correctly, being triplicated by an S3 symmetry. Is that right?
That's
Is
right.
your space-time
Yeah,
itself is being triplicated, right?
that's right. Yeah, and so the vacuum picks a particular mapping, and this is the idea anyway. The vacuum picks a particular mapping of the three, and which is, you know, sort of off kilter, and then those are the little angles, if you will, between the different versions under S3, and that breaks the symmetry. So that's what I'm currently working on. It's getting the details of that, but that's right. So I think if you put in space-time, but make it overlap so that you're not adding more generators or expanding your space, but using at least part of it as part of space-time, that may work to break the symmetry between the different generations.
Yes, that's a really interesting idea, and that also comes back to the question before: how do you include the space-time? And so I've been thinking about how do I do it in such a way that it isn't triplicated by S3, whereas you're saying no, you should have it triplicated. Now I don't know, like what does that mean if you have a space-time that is not invariant under your S3 symmetry? Like physically, how should I think about that?
Well, so you end up having to force it, right? I mean, you do need it to be symmetric so that the space-time itself is the same, but that break of symmetry then manifests in the fiber itself. So the fiber has to adjust its orientation in space-time to compensate so that Lorentz invariance is maintained, but you know that then generates a different profile that these so the electroweak has to sit at the same sort of side of the algebra as space-time does, because that's where all of this happens, right? That's where all of the masses and whatnot are generated, and CKM and everything. So strong force can't see any of this. It shouldn't be aware of any of this kind of stuff. I mean, we want to maintain full symmetry there, but if you put it on the same side as electroweak, then there's this dance that happens between the two of them that creates the breakage.
That certainly is very interesting because there's obviously in the model I have, there's obviously room in terms of doing more right actions that would be invariant under S3. That's possible, I think, in general. And so maybe there is space there to have the space-time or the Lorentz symmetries. Then they maybe wouldn't be invariant under S3. But it's also interesting in terms of the work that Tejinder's been working on, and Antonino and myself have also discussed a little bit, which is about gravity-weak unification, or merging the space-time and the weak symmetries together. So that would look that's quite similar to what I think you're describing here, is where you have the weak and the space-time is from one side, right? And then it's blind to this SU3, and that's because this SU3 is acting from the other side.
Right. So U3 has 9, right? Nine different, eight of which are the strong, and then you have one U1 in there.
Yeah.
When you flip it to the other side, you would have the same set of bivectors, but space-time comes in over, at least in this is the model that I have, overlaps, and so it breaks it down to U2, which gives you 4, and then you have 5 additional, which are cosets. So
yes, okay.
The cosets are the Higgs. It's U3 over U2. So, and you get an SU2 doublet, which is 4 of them, and then a dilaton as well. So you have one extra that you have to accommodate for, but it breaks perfectly into that structure.
That's great. That sounds fantastic. I'll have to go back to your paper, and we'll have to keep the conversation going sometime, because I think this may well be the best way to do that and to incorporate it into what I've done. So thank you very much.
Thank you, Jason, for that very interesting discussion. Anything more, Jason? If not, then
no.
okay. Thank you, Lyle. Please go ahead.
Hello. I was wondering if you're, probably you are, but familiar with Lomas and Paul and Sorgsep's non-associative algebras in physics. They have
Yes.
a chapter, right, devoted to ternary sedenions and bimodule representations. And so you were asking about more room on the right multiplications. If you're looking for ideas, you might look at their work. So.
Yes. That's a great book. And especially like in
Niels,
the
sorry, Niels, could you remind us, either of you, which book was that?
I think it's called
Non-associative algebras in physics. Yeah.
That's it. Lomas, Sorgsep, and
Paul or Powell. Yeah.
Powell,
Oh,
yeah.
great. I'll look it up. Thank you. I think I was not aware. I'm sorry.
They were very active in the 90s, I would say that, or well, and before that.
Mhm.
Yes,
Great.
and especially later on in the book, they have a really nice representation of like the left actions of sedenions and right actions of sedenions, written in terms of 2 by 2 matrices of octonian left actions and octonian right actions.
Yes,
It's really quite nice.
Thank you for that reference. I think the community would like to look it up. Anything more, Lyle?
No, thanks.
Thank you. Antonino, good to see you. Please go ahead.
Thank you. Thank you, Niels. It was a great talk. I'd
you.
like to ask a little bit about, you say this S3 selection, which is not imposed by hand. If you can comment more about that, because I find it extremely interesting.
Well, in the way I see it, it's not imposed by hand because let's go back here. So if you apply the Cayley-Dickson process to the real numbers, you can generate all the division algebras that way. Are you happy with that?
Yeah, I think, I need to understand more. Maybe we can continue even discussing later about that. Because I was wondering if this could point out to some peculiarity of it can be connected somehow to a representation of a spinor representation by itself.
What do you mean by the spinor in this case? You have to be a bit careful because here we're talking about like algebraic spinors as minimal left ideals of Clifford algebras. And others like Dickson, for example, he talks about a spinor as some tensor product of division algebras. So we have to be a bit careful what do we mean by a spinor. But in terms of the S3, where it's coming from automorphisms of this algebra of sedenions. So the largest division algebra is the octonians. But this process that you can use to generate the division algebras does not stop with the octonians. So you can get ever larger algebras. And the next one after the octonians is the sedenions. But if you look at what happens to the automorphisms of all these algebras, once you get to the octonians and beyond, the derivation algebra for all of them is always G2. And the only additional structure that you seem to get is factors of this discrete group S3. So that's why if I look here at the automorphism group of the sedenions, it's got this G2 part and it's got this discrete S3 part. And so the whole motivation of my construction has been, can I use this S3 and interpret it as a family symmetry so that I can get 3 generations instead of just 1 generation, which is what a straightforward construction with octonians gives you.
Another question that somehow maybe is related to what people was discussing before, but is what we have been discussing very often as well, is about any hints, any new hints, let's say, that is relevant for the dynamics.
For the dynamic? No, that's
including the dynamics, even the mass gap generation.
well, exactly. This is the obvious thing that needs to be addressed is the dynamics, because so far this is just a kinematic model. Like it's just algebra. And if you look at the literature in algebraic unification, most of it is just group representations and algebra. What's missing at the moment is dynamics. So now I feel quite happy that the algebraic structure is set up properly. So now the next thing, that's exactly the thing to do, is to look at some dynamics to see if it tells you anything.
But you think, I mean, is there any signature besides, I mean, the one that you have been underlined, but some other signature or someone that you want to underline now that you think could be the most promising to guide toward the development of the dynamics?
But when you say signature, sorry, what do you mean by?
Oh, signature means some
indication of
feature,
it.
some
Like,
Clues.
feature, some indication.
yeah, so I think the thing that would be promising to look at is to develop this Higgs sector further and the Yukawa terms, and then look at it in a way that it's going to be invariant under this S3 symmetry. Or likewise, you can try to write down a Lagrangian by just looking at the scalar parts of all the different terms in the Clifford algebra, but then making sure that it's invariant under this family symmetry.
Yeah,
Or like invariant under the triality symmetry. But I haven't started that work yet. That's on the long list
And
of things to do.
any other invariants that you think could be used?
At this stage, I don't know, because one thing to try and do is to try and find additional constraints, because in CL10 you have quite a lot of space, and I'm only using a little bit of it. So what happens to the rest of it? Is there more structure there? Can you put more constraints in there? But that I'm not sure.
Okay, well, we can
That's too soon. But like,
let's discuss later.
yeah,
Thank
definitely.
you.
Let's discuss more.
Yeah, so there's a comment by Igor, I think. Thank you, Antonino. Igor is saying the book on non-associative algebras in physics comes from my colleagues in Estonia. And as far as I remember, it's a conference proceedings volume of 1990 held near Tartu. I don't remember if sedenions were actively discussed in our community at that time. Paul's thesis, finished around this time under supervision of Lomas, was about Mofang loops. Okay, so he's saying this is a proceedings and not a book. Okay, useful either way.
That's a different work that they put out. The actual non-associative physics and is a book that they put out.
So it's not
But
what Igor
it does have
saying.
multiple. It is arranged with each chapter has its own bibliography. But
Okay,
it is
great. So are these two different books, or they're the same?
They put out a lot of works, not just this book.
Okay, great. We'll look it up. We'll look it up. Thank you.
But in the book, they also talk about Mofang loops. So I think the book is quite comprehensive from
Yes,
memory.
I think
It's been a while since
chapter
I've looked
5
at
of
it.
theirs might do the Mofang groups. Chapter 3, I think, is the sedenions.
Oh yes, this was a question I
You
was
seem to know
also
this book really well.
Yeah.
Yeah.
Great, yeah. So Niels, Jason is asking, I also had the same question. I suppose you do have three generations of right-handed neutrinos also?
Oh, yes. Yeah, I should have specified that. Yes, there are
Yeah.
all two generations of right-handed
It's
neutrinos.
interesting that this is one thing, even though I come at it differently, we both agree on two Higgs, and of course everybody gets three right-handed neutrinos. I also have two Higgs, so coming in a different language. So I had a question for you. CL6 was related to octonions, CL8 to sedenions. Then you went to CL10. Does
Yeah.
that in any way correspond to going to the next step beyond sedenions in the Cayley-Dickson
Well,
process?
look, yes. If you want to, you can keep doing that indefinitely, right? Because each time you apply the Cayley-Dickson process, you double the dimension of the algebra. So the sedenions are 16-dimensional, then the next algebra would be 32-dimensional. And then, of course, if you take 32 by 32 matrices, it'll give you CL10. But
go ahead.
But I don't see that as being very sensible. To me, it make more sense to say include a couple of the quaternions, for example. So instead of looking at C or complex sedenions, include a copy of the quaternions. So you got C cross H cross S. And then it's a direct generalization of what Jeffrey Dixon has done, because he looks at C cross H cross O. So I'm saying, well, just replace the O with an S. And then you would have that, because if you look at,
Okay.
And then that also then gives away, if you needed to go to CL12, because for the quaternions, the left actions are different from the right actions. It gives you two different copies of CL2.
Right. Yes, no, I was just thinking, just for completeness, we could give a name corresponding to sedenions for CL10. I don't know what they are called.
Well, I think a name does exist for it, but I don't I wouldn't want to really put that in any paper.
Okay, great. Thank you. Also, just a small comment on what Anthony and you were discussing. I at least don't know how to get to mass ratios or dynamics without extending the standard model. My picture is that the representation theory kinematics that we all do so far is telling us how to organize the standard model. But if mass ratios were to be derivable from the standard model itself, my naive picture is it would have happened by now. What is it that this kinematical organization is telling us about the dynamics, which the standard model does not already know through quantum field theory?
Well, I think indeed that is the pressing question. I think that's exactly, if I understood it right, that's what Antonina was saying as well. Like, okay, so if we have this, what does it mean for the dynamics? And I don't have an answer for that at the
My
moment.
answer to that is that to get a meaning which is not already in the standard model, we need to extend the standard model at least by a U1, which will have another quantum of charge which is not electric charge, because we have to break somehow the degeneracy between flavor states and something which carries information about mass. In the standard model, there's no quantum of mass. I mean, it's a Casimir in special relativity coming from classical mechanics. It has nothing directly to do with quantum mechanics. So if I want to quantize mass, which is what the mass hierarchy is, it's a quantization of mass. If I want to quantize mass, I need an operator in a generalization of the standard model whose eigenvalues are mass numbers. I'm just telling my picture that
Yeah, okay, but have you checked if you include an additional U1, does that become possible?
that's what my work is. I mean, that's what the UN defines the square root of mass quantum number. And I deliberately, and I can motivate it from theory, I'll assign a mass number of 1 by 3 to the electron family and 1 to the down quark family. And then I do the exceptional Jordan algebra eigenvalue problem. And there's a mismatch between these U1 determined mass eigenstates and flavor eigenstates. And that is where the mass ratios come from. To put a long story short, I'm saying we need some quantum of mass, which is not there in the standard model.
Yeah, okay. So if I I think that the paper you're talking about is your paper you wrote quite a few years ago now, right? It's quite a long one as
Yeah,
well.
but yeah, I updated it last year. It's called Fermion mass ratios from the exceptional Jordan algebra. It is a better version of the older paper. It's close in spirit to what Gonzalo is also doing, except that we had this little bit of discussion with him that something more will be needed to convert those his numbers into mass ratios. So that's where I'm going to get back to you, Niels. We should discuss this. How does this, what you do with your S3 symmetry, how does it compare with the exceptional Jordan algebra, which builds on the triality of spinate? Well, I mean, some people are motivating that as a reason for three generations and accommodate three generations in the 3 by 3 exceptional Jordan algebra matrices. Yours is one way. Are these completely independent, which looks unlikely? If both are correct, then they should be related. And both, this looks solid what you're saying. But the exceptional Jordan algebra also seems well motivated. So we should try to understand how these two are related to each other.
Yeah, well, I didn't even touch upon the exceptional Jordan algebra here, but yes, I'm well familiar with those constructions. I think at the end of the day, uh, the different approaches, whether you take my approach here based on sedenions, or if you look at triality or at the exceptional Jordan algebra, I suspect it all comes down to ultimately the same thing.
I agree.
I
I
think you'll
agree.
be able to map one model to another model.
And we should do that. I think it would help understand better if we do the mapping. But
Yeah, well,
yeah,
that's why I pointed it out at the end. It's like at the moment I don't see how the S3 that I'm using is related to the S3 that you get from triality,
yeah,
for example. It's
yeah,
slightly it's different. I don't think it's the
yeah.
same S3. And
No,
if
it's
it's
not. As such, it is not. But if both are describing three generations, then there has to be some connection between them.
yes, I agree. And the same if you look at the exceptional Jordan algebra, you have three generations inside there. Each generation is depends on one of the octonions.
Right, right.
So
And it
you have
utilizes,
three copies of octonions inside the exceptional Jordan
right, that's
algebra.
correct. That's correct.
And each generation is to be a smaller Jordan algebra, the 2 by 2 one,
Yes.
which is not exceptional. That only depends on one octonion. And so there's
Yeah.
three such smaller sub-algebras
And that
inside
that
that make
perhaps I
them.
think, yeah, that can be related to CL6, I think, the 2 by 2. But we can come back to that, yeah. My main point is that I talked that also with Gonzalo and Anthony, that we need two copies of the algebra. Like say if you have one CL6 for let's say flavor eigenstates, we are going to need one more CL6 for what I call mass eigenstates. And these two are selected when the both have a S3 symmetry, which before breaking the two S3s are identical. After breaking, the flavor states select one vacuum, the mass eigenstates select a different vacuum. That mismatch will give mass ratios. At least I don't know how, without choosing two different vacua, how one can break them and get the mass hierarchy. Because before symmetry breaking, all the three generations are identical, and if we can define mass, they would have identical mass. And after symmetry breaking, the flavor eigenstates are they are having the same electric charge. Electric charge is the same for three generations, only the masses are different. That suggests that electric charge and mass are two different quantum numbers arising after the S3 symmetry breaking, and we are in the flavor basis, we are in the electric charge basis, but which is in which basis the mass numbers are not the same.
Yes. Well, okay, there's a lot to unpack there. I think if you want to take two copies of the algebra, of course you can do that, and anyone is free to take as many copies as they like. For me, I'm trying to keep everything as small as possible.
Yeah, so Niels,
Already I was annoyed when I could not get everything within CL8 the way I wanted, and I was ultimately
so
forced to go to CL10.
my way of looking at it is, Niels, that you are keeping it too small. It's risky. You have to make it little
Yeah,
bigger for it to yield what we want.
but the challenge is to keep it as small as possible.
Yeah, but we
It's a
might be
puzzle.
missing. I'm saying we might be missing out something.
Yeah, but I think to get a deep understanding, you have to play around with something as small as possible.
That I agree. That I
It took me
totally
a long
agree.
time to actually understand why CL8 was not going to work with my construction,
Hmm.
and that I must go to CL10. But now I understand that much better. So,
I,
but now if you're
I
saying, oh,
agree.
we should take two copies of it, well, I don't really see any motivation for that. I understand, like at the end of the day, you want to be able to reduce the number of free parameters in the standard model, right? That's where you take this.
The way I motivated two copies, I associated different chiralities with them. One chirality with one copy, another chirality with the other copy. But anyway, we can come back. Anthony has a question. Anthony, go ahead, please.
Yeah, it was just to react to the point about trying to do things with as small a set of equipment as possible. So just in terms of what I've been doing for some years, I'm starting with the space-time algebra, so just the algebra of ordinary 4D space-time. And what I've been finding over the last 2 or 3 years is that inevitably leads me to the sedenions, and I can represent a lot of the structures you're talking about here because they're CL8 in purely space-time algebra terms, which is nice to see it sort of homing in on the sort of thing you're already doing. Um, the only reason at the moment I think I need to go to CL10 is actually to get imaginaries coming in, because the space-time algebra being wholly real doesn't
Yeah.
allow that. But CL10, then you've got plenty of things you can sort of pull down to the 8D, which give you imaginaries. So that's just to say one can do quite a lot with really quite minimal equipment, but I would certainly give strong support to the Sedenium program here. I think it's no, it's exactly what I'm finding.
Thank you, Anthony. If could I push you a little bit in one of your recent emails, you said you're close to understanding mass ratios. Would you like to reveal a little bit?
I'm
You
not
stay
sure I
within.
actually
I
said
just
that.
want to ask, do you stay within the standard model?
Yeah, so I don't believe that I'm close to understanding the mass ratios. What I think I'm close to is understanding how your Jordan algebra approach relates to the it can be put under the STA way of doing things.
Mhm.
So
That would be great. That would be
yeah.
great. Yes.
So it's a unification in that sense of three
Okay.
different approaches.
That would also answer Neil's query about relating his S3 to spinate, I think.
Yes. I mean, it seems to me that surely this is something I find surprising. Surely there must be some mathematicians who might be able to help with this. It's not just a physics question. This is very much a maths question.
Yeah,
Is
Yes.
this S3?
yeah, sorry. So go ahead, please. Go ahead.
Yeah. Is this S3? Can we use it to give triality?
Yeah, if you don't mind, these days I'm quite addicted to what Claude and Fable 5 do. So while Niels was giving his talk, Niels, if you don't mind, can you stop sharing for a minute? I'll show you something. So
Is that okay? I think I'll stop sharing.
yeah. So what I will do, yes, no, not Claude. I don't want to share. Sorry to be clumsy, but I want to show you all something. How do I stop sharing? Okay.
Well, maybe in the meantime, I can make one comment about the mathematics and
Yeah,
triality.
I'm there. Yeah, can you all see the screen? I just asked the machine to compare the exceptional Jordan algebra with the S3 of Niels. So I haven't seen the paper, but it's this quick. These guys, the computer can, the AI
Yeah,
can
but
do a lot. This is all a one command product. I'll share it with whoever is interested. So it claims to know the answer that Anthony was asking to ask a mathematician. So I'll share it with you. I mean, I don't know if it's correct, but it claims to know. Sorry, go ahead.
well,
Jason?
there's one interesting mathematical result in a paper. Maybe this is well known, but I think it's really nice. Is that if you look at spin 8, there's a unique way in which you can choose 3 spin 7 subgroups such that their common intersection is G2, and the 3 spin 7 subgroups are permuted by S3. Now, I think that must somehow be related to what I'm doing here as well.
Mhm.
I'd be very surprised if that seems to be where each generation must somehow be within this spin 7 structure or something.
Spin 7.
Yeah, spin 7 subgroup of spin 8. And then
Mhm.
there's an S3 symmetry that permutes between them, the 3 spin 7 subgroups. And there's a unique way to do it so that the common intersection of the 3 spin 7 subgroups is G2.
Do you already have chiral fermions, or does that wait for the Lorentz structure to be switched on?
I think that needs the Lorentz structure to do it properly.
Mhm.
So, but I think this comes back to the discussions we've had in the past about this gravy-weak unification, because I think that's also somehow related, and also
Right.
to what Jason was saying before. So I think
Mhm.
you want to do maybe the answer is that you want to do two different things. You want to do gravy-weak unification, and at the same time, whereas the weak part might initially be invariant under this S3 symmetry, it might be that the space-time part, the gravity part, is not. And then
Yeah,
that you force
right.
it to be exactly in the way that Jason's been talking about, and then that gives you this extra structure.
Yeah, so that's precisely close to what I'm saying. When there is gravity-weak unification, there are essentially two copies of S3, one for weak, one for gravity, both are identical. And when the symmetry breaks, the S3 that goes with weak is different from the S3 that goes with gravity. And that's what creates the mass hierarchy. But notice that this involves going beyond the standard model, right? I have to bring in gravity or something equivalent.
Right.
Look, we're gonna need more than just raw gravity anyway, right? I mean, because the thing isn't renormalizable. I mean, you can,
Yeah, that's where the U1 comes in. So I have
yeah,
SU2L cross U1Y, that's electroweak, and SU2R cross a U1Y prime. The SU2R becomes gravity, general relativity, and U1Y prime is the one that carries square root mass quantum number, which is what I was advocating for. So yes, you are absolutely right. Electroweak and what I call a gravi-dem. The U1, you get, Jason, what I'm saying.
yeah, yeah. It's brilliant.
Right. Yeah, because
Well,
gravi-weak has to, sorry, gravi-weak has to respect electroweak also. Sorry, Niels, go ahead.
well, actually, I have one question for Jason. about this, if I remember correctly, because it's been a while since I read your paper, but you, at some stage, I think you're working in CL6, and then you choose a Lorentz spacetime inside that, but they're not, the gamma matrices are not simply four of the generating basis elements of the Clifford algebra. Am I remembering that correctly?
Yeah, so that paper was an attempt to model the standard model in the absolute smallest possible Clifford algebra that you needed to do so, just to show that it could be done.
Yeah.
And so CL6 is the smallest that you can do and make it work. And you're right, the mapping, all four of the space-time gammas were mapped it's a very complex map
Yeah.
into the Wick generators from the fiber. So the fiber and space-time basically overlap on each other completely in that model. Now I've got a CL8 version where it's much simpler map between the two, and it still works. The disadvantage is it creates mirror states. So you have one generation built in terms of the number of states, but then you have a mirror set. Now there is a overall master U1 that has the property that it pushes out the mirror states into super high masses. So I've managed to solve that problem, but yeah, I mean the fundamental mechanism by which all of this happens is that mapping, because that creates a break, because you have a left side or right side multiplication. I do the flip of what you do, so I put the weak on the left instead of the right, but same basic thing, same idea. And so gravity hits it, and and that breaks what would have been U3 down to U2, because you still have those degrees of freedom. And then all of that extra structure is still there. It just manifests as scalars instead of vector bosons, which end up being the Higgs field. So the Higgs field comes out of that same mechanism. I don't have to insert it extra, but I also get an extra U1 in there as part of that coset. So because it's 5 cosets and 4 of them are the Higgs, right? Does it make the Higgs doublet? So you have an extra U1, which I haven't done much with, but it lays right on top of the pure gravity direction. It manifests as if it were part of the gravity, if that makes sense. So,
Jason, I would request you to please see my papers also, because I think we are doing very similar things. In particular, at some stage, we would also like to unify the fiber with the Lorentz structure, right? That would be true unification. And that is in principle possible, I think, in your U3, U2 language. The U2 part gives gravity, and what remains can be related to the internal fiber.
Correct.
But where I think this is also interesting is because the paper, the CL6 paper, Jason, where you identify gamma 1, gamma 2, gamma 3, and gamma 4, that's not a maximal set. I'm pretty sure you can get a 6-dimensional spacetime.
Yes,
And
exactly.
And the reason,
you hit on what I'm working on. Yeah, exactly.
Okay.
Yep.
Because it's not obvious, right? Because the way that your gamma 1 is a complicated expression in terms of the basis elements of CL6. So it's not obvious that you can get a 6-dimensional spacetime that way. But I remember a few months ago, I sat down and I was able to find 2 more gamma matrices that anti-commuted with all of them, and so give you a 6-dimensional spacetime.
Fantastic.
And I think that's really interesting because of what we've been discussing for a few years now with Tejinder about the Gravi-Wick unification, which is also like a 6-dimensional spacetime. So I think it all ties those ideas together.
Right.
Yeah, and then there was just a similar S3 rotate for the different generations, because the mapping, your fiber has 3 complex dimensions, alpha 1, 2, and 3, and you just cycle through them, and it creates 3 different maps. And then the vacuum just picks like one direction, so to speak, between the 3 and says that's space-time. That, you know, of the three sets, that's the real one, but it doesn't quite line up with those three base sets. So the generations are tilted off of regular space-time, which produces different couplings for the Higgs. The coset doesn't, you know, it doesn't line up. And that's the basic mechanism by which to produce different masses in a mass hierarchy. Now, I managed to get it down to, I have one massive generation, which works great. And I can get a hierarchy in the lepton sector, but I can't on quarks. So that's what I've been working on recently. Is, you know, one of the disadvantages of the system is that quarks are defined on the opposite side of where the weak force acts on the left. You know, you determine the quarks on the right side. So it's like, well, how do I break the symmetry here so that the quarks get a different mass than the leptons? And I haven't figured that one out yet. So still working on it.
In the division algebra language, I can restrict leptons to the quaternionic subalgebra, and quarks need octonions. The quaternions are adequate for neutrinos and electrons. And then, of course, for three families, you have to go to triality. I had a question for you, Gonzalo. You talk of three generations from CL8 and spin8, right? Is that correct?
4, actually.
Four, yeah, four
Four.
generations. But by staying within CL8.
So within CL8, I get 4 generations. 3 of them mix, the 4th one doesn't, basically.
So
and you can get Lorentz transformations, the full standard model gauge group, and an additional family force. So it's like it's a counterpart. For every internal transformation, there's a mirroring external transformation, and the interpretation is different.
So Niels, you go somewhere else from CL8, and Gonzalo's doing something different with CL8. So from my limited understanding, where do you differ?
It's a big algebra. You can do a lot of things with CL8. It's a very big algebra. Yeah.
Okay, yeah.
You can do a lot of things there.
I think the main differences are that I'm not starting with triality. I'm starting with an S3 symmetry. Now, it could be that is I suspect is very closely related to triality. I just don't understand at the moment how. And the other thing I think that's different is that I'm starting with a commutator action, and I force it to become a one-sided action. And I think then I cannot do it in CL8. What's that, sorry?
So that's where it's really different. So when you impose the commutator to give a set of ideals in the same space, you strongly restrict the available things that you can do with CL8.
Yes, that's right.
Good on one side, because you're basically, so you're imposing a rotor transformation, right? When you consider just Clifford-algebraic. And that kind of already breaks the symmetries. If you consider just one-sided transformations, like a bispinor, right? Like different transformations from the left and the right-hand side.
Yeah.
And you get larger symmetries, but you can't break them. You need Higgs fields to do that.
Yes.
That's the main difference.
Right.
That's why you need larger algebras if you want larger symmetries.
Yeah. I think that all makes sense. So I think that's where currently what we're doing is different, but I think ultimately it's very closely related.
Definitely.
And I think the S3 that I have must be related to the triality you are using.
Oh yeah, for sure. Yeah.
I just don't see exactly how, but yeah, I think it's. But then
I think
you say you have a 4th generation.
Yeah. So the diagram that you get is so what's important here is not octonions or quaternions, is the spin8 representations, the available different ones. You have 3 with dimension 8 and 1 with dimension 38, right? So triality permutes the dimension 8 representations. The 4th one is in the middle, is the adjoint, is unaffected by these transformations. And this SU3 that rotates these 3 transformations is responsible both for the family symmetry, acting just on 3 generations, and the strong force. So the thing that breaks this symmetry, right, the SU4 into the SU3, is fixing a triality. like you fix a D4 LinkedIn diagram. But you get 4 generations, not 3.
But are the 4 generations linearly independent?
Yes, all of them.
Wow.
That comes out of the Dirac-Lagrangian.
Okay,
Because of the
I
Dirac-Lagrangian.
thought like maybe what could be the case is, for example, if you take a sum of my 3 generations, that would be invariant under this S3 symmetry, and you could look at it as a 4th generation, but it would no longer be linearly independent. So I'm basically saying you could put anything into the S3 symmetric representation, into the singlet representation. But you're saying that's not what you've done. This is different.
No, it's different. Yeah.
Very interesting.
It's different, and it's because I take different left and right-handed transformations, so I allow for that freedom. Because initially I was doing like you were doing, so I only got, even then, I mean, even using the commutator, you still get 4 generations, but the symmetries that you end up getting in the external viewpoint is no longer Lorentz transformation, and I didn't like that. So that's why I kept freedom from left and right transformations.
Very nice. Yeah, definitely nice work.
I still have to update the archive link though.
Yes, please share it with me when you upload it.
Yes, of course. Yeah.
I look forward to reading it.
Okay, great. Thank you all. Any more questions or comments, please?
I would like just to thank very much. Thank you very much, Niels, for all your helpful comments and your helpful explanations when I was working on those verifying your papers.
You're very welcome, and thank you for taking the time to verify them. It's really nice to have this independent verification.
Yeah, I wanted to understand what you are doing, and I thought that this is the best way to do this.
Well, thank you very much, because it really benefited me a lot, and it's nice to be able to share that link also in the archive paper, so that anyone can check for themselves very quickly that everything works.
Yes, thank you.
Yes, and let us stay in touch.
Yes, we will.
Definitely. Thanks for your comment.
Okay, great. Niels, thank you once again for a beautiful lecture, which led to all this very stimulating discussion. You were right in the morning when we talked that it is for this discussion that these talks should continue. We get to meet here.
I think so. Yeah, like the talks, well, anyone can read a paper, right? And you can get more or less the same idea, but it's all being, well, at least online in the same place and being able to ask questions and discuss and connect different ideas. I think that's where the real value lies of these.
I agree. Yeah, so that spirit, motivation for continuing next year. So we have a break in August. Enjoy your holidays, please. And we'll meet on September 3 for Andrew's talk on geometric algebra and supersymmetry. Very much looking forward to that.
Jinder, can I just come in? Sorry, I just wanted to say I was able to join for the last 20 minutes or so.
Oh,